Hi there. This is a continuation of our discussion of the precise definition of the limit series of videos. This is part 2, so we're going to continue with this example. Prove that the limit as x goes to 1 of x squared minus 2x is equal to -1. First off, make sure that the limit is actually true. You can't prove something that's not true. So just quickly play it in. So when you have 1, you're going to have 1 squared minus 2 times 1. So that does give you -1. So I know that that limit is true, so that is something that we'll be able to prove. Based on the previous video, now I know that there are 3 things I should find. I need to figure out what my a is, what our f of x is, and what our limit is, what our L is. So a, the limit as x goes to 1, and the definition, this is the limit as x goes to a, so a must be 1. Our function is what are we taking the limit of, so that's our f of x, so x squared minus 2x, and then what it equals, the limit to L is -1. And so we're gonna go into then the body of our proof. And you can do the scratch work first and then come back and write the proof. I kind of write what the body of the proof is going to be and then do my scratch work so that I know what things I'm looking for, but you can do it in any order. So my proof is, for the definition says for any epsilon greater than 0. So I'm going to say let epsilon greater than 0 be given. Right, so we're given any epsilon, we have to find a delta. So given a particular epsilon, we're going to find a delta. So we're going to choose delta to be something. This is where our scratch work is going to come in. And then we're going to assume the if statement from the definition. So we're going to assume that the absolute value between x and a, the distance between x and a, so x and 1, so the absolute value of x minus 1 is less than whatever our delta is. Then, right, so a proof, we are proving an if-then statement. So if this is true, so we're going to assume that it's true, then the result follows. So then f of x minus L in our case is our function f of x, which is x squared minus 2x, and then minus L. L is -1. And so we can simplify this. So x squared minus 2x plus 1. And so then I need to figure out, okay, what is this? So, but I need to find the delta. So let's go do our scratch work. How do we start the scratch work? We start with what we want to prove. So we want the absolute value of f of x minus L to be less than epsilon. That's what we want. So at the end of this proof, we're saying given any epsilon, I can find the corresponding delta so that then f of x minus L will be, my goal here is to say that this equals is going to change to a less than and have just epsilon. So that is the goal. So we're going to go back to our scratch work here. So we want f of x minus L less than epsilon. So I'm going to just start doing my scratch work. So f of x, x squared minus 2x minus L, so minus a minus 1, less than epsilon, and then, so I have this so far. And so now I have to figure out how do I handle this. This is different than when I had a linear. With the linear equation, I could just, usually it was just off by a constant, right? The other thing that I'm hoping to see is that my x minus a, my x minus 1 shows up in here. So with the linear function, it's a lot easier to see than with a quadratic. But let's see, it's a quadratic, so can I factor it? Can I factor it into 2 quantities? So 2 numbers are multiplied with +1 and add up to -2, yeah, -1 and -1. Right, so then this actually, there's my x minus a. So as soon as you see your x minus a absolute value, you should smile. We're doing something right. And so I can rewrite this as the absolute value of x minus 1 squared, since it's x minus 1 times x minus 1, that's less than epsilon. And now the goal is to just get the absolute value of x minus 1 by itself. Right now I have the absolute value of x minus 1 squared. So how do I get rid of that square? We can take the square root. And the reason that I can take the square root here is, without messing up the inequality, is this is already absolute value. So I'm going to have positive, and then on top of it is being squared. So this is definitely a positive number. And so when I take the square root, I don't have to worry about having to do multiple cases because I already have something positive in there. So this is just going to be the absolute value of x minus 1 less than the square root of epsilon. And so now that I see, oh, there's my x minus a, and I have it less than that something, so that something is my delta. So we're going to say delta equals the square root of epsilon. So the scratch work is for any epsilon, I can find the corresponding delta. So now we go back to our proof. Now that we know how to choose delta, we're going to go back and say, okay, let epsilon greater than 0 be given. Choose delta to equal the square root of epsilon. And then assume 0 is less than absolute value of x minus 1 less than the square root of epsilon. Then this happens, then f of x minus l is equal to, and this is where we stop. So now we continue, keeping in mind that our goal is to get the whole thing is less than epsilon. So now I know that this is x minus 1 quantity squared, and now we can use our assumption. Because x minus 1, the absolute value of x minus 1 is less than the square root of epsilon, this whole thing is going to be less than the square root of epsilon square, right? And that's why can I say that? Because this, right? So I can say since the absolute value of x minus 1 is less than the square root of epsilon, I can then replace that absolute value of x minus 1 with the square root of epsilon. If you're a little confused with that, let me just do a quick example. So if I say, if, let me pick some random variable, say w is less than 5, what can you say about 4 times w? Right? If w is less than 5, then I can say 4 times w then is less than 20. Because I can say, well, since w is less than 5, I can replace that w with 5 and say 4 times w is going to be less than 20. So that's kind of what I'm doing here, right? So if I say, same thing, so let's do that, 1, 2. So if w is less than 5, what can you say about w squared? Then w squared is going to be less than 25, right? And so that's what I'm doing here. So since the absolute value of x minus 1 is less than the square root of epsilon, I can replace the absolute value of x minus 1 with the square root of epsilon. So then the absolute value of x minus 1 squared is less than the square root of epsilon squared. But then the square and the square root undo each other. So I'm just left with epsilon. Therefore, we were able to prove that f of x minus l is less than epsilon. And we're done with that proof. These proofs become a little bit harder when you don't end up with the perfect square here. So if this had factor into, for example, x minus 1 times like x plus 2, then I have to do a little bit something different with that extra term in order to bound my delta. All right, let's try another example. Let's try this next example. Use the precise definition of the limit to prove that the limit as x goes to 2 of this rational function is 3. So first of all, check, is it true? So let's check. The limit as x goes to 2. When you first plug it in, what do you get? On the bottom, you're going to get 0. So let's see, 4 minus 2 minus 2, so you're going to get 0 also. So this is 0 over 0. So what does 0 over 0 mean for a limit? Do some algebra. So the algebra we're going to do here is factor. Two numbers are multiplied in -2, so x minus 2 and x plus 1. So those cancel, so that means we have a hole in the graph. The limit ends up being the limit as x goes to 2 of x plus 1, which then plug in 2, you get 3. So is it true? Yes, it checks, so that means I can prove it, right? If you're asked to prove something that is false, you're going to run into some issues when you're trying to do the proof, like a delta is not going to come out. So make sure that you're proving something that is true. Okay, so what is our definition of the limit? So let's write it down. So the limit as x goes to a of f of x equals L means that for any epsilon greater than 0, there is a corresponding delta such that if, this is our big if statement, right? If 0 is less than x minus a less than delta, then, or if then statement, then the distance between the y values and the limit is less than epsilon. So for any epsilon greater than 0, so we're going to pick random values of epsilon that are really, really, really small. There is then, for any epsilon that people give you, there's going to be a corresponding delta. So our task is to find that delta such that then if the distance between x and a is less than delta, the y values and the limit are within epsilon of each other. All right, so then what do we need? We need to figure out what is a, what is f of x, and what is L. So looking back at our function, our a is 2, limit as x goes to a, so a is 2. F of x is this rational function, and the limit is 3. So a is 2, L is 3, and f of x, I remember this was x minus 2. Let's scroll back up, x squared minus x minus 2. So that's what I need for my definition. And as I mentioned in the first video, make sure that you memorize a definition or have a 3x5 note card that you can access so that you can have the definition ready. So we're going to start the body of the proof. And as I mentioned for the previous example, you can do the scratch work first if you prefer that. So we're going to say let epsilon greater than 0 be given. Right, that is the part of the definition that says for any epsilon greater than 0. So let an epsilon be given. Then there is a delta greater than 0. So for that particular epsilon that you're given, you're going to find the corresponding delta. Be given, so we're going to choose delta to equal something from our scratch work. And then we're going to make our if-then statement. So we're going to assume that 0 is less than the distance between x and a was 2, less than whatever we choose our delta to be. So a is 2, and then f of x is that, and L is 3. So then the absolute value of f of x minus L is equal to, and in our case is x squared minus x minus 2 over x minus 2. Right, that's our f of x minus L. L is 3 equals, and then we're going to continue the body of the proof. So let's go to our scratch work to find delta. So what is it that we want? We want f of x minus L in absolute value to be less than epsilon. And so let's see what that means. So f of x, x squared minus x minus 2 over x minus 2 minus 3 less than epsilon. I could find a common denominator here, right? Put that over 1 and do a common denominator, but when I checked to see whether this limit was true, I noticed that I can factor this. So that's what I'm going to do. Instead of making extra work for myself and finding a common denominator, I'm just going to reduce that. I know this factors into x minus 2x plus 1 over x minus 2. And I have minus 3 less than epsilon. And I know these cancel, so I have the absolute value of x plus 1 minus 3 less than epsilon. And this becomes the absolute value of x minus 2 less than epsilon. So now notice that, hey, there's my x minus a. Hey, there's my x minus a. So at this point, we should be happy. We are doing something wrong. If I don't get my x minus a in this scratch work, I've done an algebra mistake somewhere along the way. And I already have the absolute value by itself, less than epsilon, so I'm just going to choose delta to be the same as epsilon. So let's go back to our proof. Let epsilon greater than 0 be given, choose delta to be the same as epsilon. And we're going to assume then that our absolute value is greater than 0 but less than epsilon. And then this happens. So let's continue to simplify this. We redo our work, right? So then I already know that this reduces to x plus 1 minus 3, which is the absolute value of x minus 2, which I already know then that's less than delta, which is epsilon. So that's less than epsilon, and our proof is done. So this one, even though we started as a quadratic and something that looked intimidating, the fact that that term cancels out, it leaves us with a linear function, which linears are nice. So the previous quadratic that we did, this one, was not so nice, but luckily for us, it factored into a perfect square. And so we can do that. Let's see. The problem that I left you with the last video to do. So let's go over that one real quick. All right, so this is a problem that in the part 1 of this video series, I asked you to try it on your own. So prove that the limit as x goes to negative 2 of 3x plus 7 is equal to 1. Is it true? Yes. 3 times negative 2 is negative 6 plus 7 gives us 1. So that is true. So therefore I can prove it. So for the definition, I need a, I need f of x, and I need L. So a is negative 2. F of x is 3x plus 7, and L is 1. And so I'm going to put the body of my proof first, and then do the scratch work. So I'm going to say, right, the definition says for any epsilon greater than 0, there is a delta. So I'm going to say let epsilon greater than 0 be given, right? Someone gives you an epsilon, you're supposed to find the corresponding delta. So that's what it means to say for any epsilon greater than 0, there is a delta. So now we're going to choose delta to equal something that's going to come from our scratch work. And we're going to make the if-then statement. So if something is true, then something happens. So if the something is true, we're going to assume that it is true. So assume that the distance between x and a, so x minus a minus 2, is less than whatever our delta becomes. So that means this is the absolute value of x plus 2 less than whatever our delta. So there's my x minus a. So my goal is, I hope to see this in my scratch work. What should I say here? Goal shows up in Scratch. If it doesn't, you've done something wrong in your scratch work. So assume that that's true, then f of x minus L, in our case, is, what is f of x? 3x plus 7, and L is 1. So f of x minus L. So 3x plus 7 minus 1 equals, and we'll go through the work in here. So let's find our delta. What is delta? So let's go to our scratch work. With our scratch work, we start with what we want. So we want the absolute value of f of x minus L to be less than epsilon. So that means we want 3x plus 7 minus 1 to be less than epsilon. So that tells me, what is this? 3x plus 7 minus 1 is plus 6, less than epsilon. Factor out a 3, so 3 times the absolute value of x plus 2 is less than epsilon. And remember our goal, we want the x minus a to show up on our scratch work. And sure enough, there it is. Absolute value of x plus 2, absolute value of x plus 2. But it's not by itself, so you need to get it by itself. So divide by 3. 3 is positive, so we don't have to worry about the inequality switching signs. So the absolute value of x plus 2 then is less than epsilon over 3. So what's your delta? We're going to choose delta to be epsilon over 3. And so now we go back to our proof and say choose delta to be epsilon over 3. Then we're going to assume that if the distance between x and a, the distance between x and negative 2 is less than epsilon over 3, then what happens to our f of x minus L? What happens to the distance between the y values and the what we're saying is the limit? Then this becomes 3x plus 6, and same thing, we can factor out the 3, and then the absolute value of 3 is just 3. And now I have, oh, there's my x minus 2, and the assumption is that this is less than epsilon over 3. So it becomes, then this is, sorry, not equals, less than 3 times, and this is less than epsilon over 3, so I can replace it with that. This is going back to that like 4 times w, that example that I quickly did over here somewhere. If w is less than 5, what can you say about 4 times w? It's less than 20. So that's the same thing that I am doing here. X plus 2 is less than epsilon over 3, so what can you say about 3 times absolute value of x plus 2? Well, that's going to be less than 3 times epsilon over 3. And our 3's can cancel, leaving us with just epsilon. So I have f of x minus L. Let me highlight that. F of x minus L is less than epsilon. So therefore, we have proved the limit. That's a symbol to indicate that the proof is done. Sometimes people write QED, Latin for that was to be proven. Sometimes people write a little box filled in, and these are ways to indicate that the proof has been proven. Okay, email me if you have any questions. I encourage you to start doing your homework for section 2.4 as soon as possible, and I'll be checking my email for questions on this section.